And with that, I think we should be live. Stefan, do you already check the audio? Does it work? Do we see the video? I see thumbs up. That's awesome. Wow, what a feeling. Not an online Rust meetup, but really a meetup in person. For all the people who watch at home, via live streaming here, we have a room full of Rustaceans. So we are very happy to have you all here in Linz, and we are very happy to have you all at home at the streaming. I hope this will be an awesome Rust meetup. And I am going to do the introduction just a few minutes. And after me, Lisa is going to kick off the evening with a great talk about embedded Rust, I think, but you will tell us more about that. So let me give you a quick introduction what we have today. Well, first, this meetup is brought to you as every Rust meetup by the Coding Club Linz. I happen to be the chairman of the Coding Club Linz. It is an honor to have this position. The Coding Club Linz is a community of IT passionate people here from Linz. Rust Meetup is just one thing that we do. The main thing that we do is Coder Dojo Linz, which is a programming club for kids. So if you have kids in Linz and they want to learn how to code and things like that, they are always very welcome in our online meetings, and I will mention that in a second. And today, I would like to say a big, big thank you to the Grand Garage. We are here in the Grand Garage, which is one of Europe's largest makerspaces, 3 or 4 stories full with awesome machines. I have no idea what these machines do because I am a programmer. I have nothing to do with hardware, but they look awesome, and people tell me that you can do crazy things with it. And we are so happy to be here in the Grand Garage. By the way, some housekeeping rules for those of you who are in the room here. I already mentioned there is a fridge full of drinks out there, and we have to drink it empty. No, just kidding. Whenever somebody is thirsty, please just take it. They are for free. That's the first thing. The second thing, the empty bottles, please do not put them in the rack out there. There is a table here in the background. Put them there, because this is the very, very simple way of counting what we have drunken, so that we can get a correct invoice from the Grand Garage. Okay, so please put it there and not there, because otherwise I'm in big trouble. So thank you thank you Grand Garage that we are allowed to be here today. Yeah, of course we started. So these are our speakers today. As I mentioned, Lisa is going to start, and then we have Tim, who is already in the audience, with a second talk, and we are looking forward to both talks here. Now, if you are new to Rust Linz, you may not already know that we have a Discord server. We mainly use the Discord server for chatting during the meetups, for sharing announcements and things like that. So if you have questions, you can type your questions in the Discord server or in the YouTube chat. You can choose. We will relay these questions to our speakers. Those of you who are in the room, of course, you can ask the questions yourself, just as you like. Now, a little bit of community news. What's going on in the IT community here in Linz? The first thing is our very own Coder Dojo Linz. Coder Dojo Linz, as I mentioned, is a programming club for kids. This week is a very, very busy week, because this week is the Ars Electronica Festival here in Linz, which is one of the oldest and prestigious and largest festivals for digital arts in the whole world. And we are present in the Create Your World section of the Ars Electronica Festival. And there we code with kids. We do some electronic tinkering with kids. So this is currently going on. The next online meetings will be next week on Friday. Next one, our friends from Female Coders. Female Coders is a community of girls and women in IT, or those who would like to get into IT and look for a community where they can learn how to code. This is Female Coders, and they are going to organize a hackathon on the 17th of September. As far as I know, the hackathon is here in the Grand Garage. So if you know women or girls in the IT who would like to join such a hackathon, they are always very welcome. And take a look at the homepage of Female Coders. You will find more information there. Next one, Stefan, Stahlstadt. There will be a Stahlstadt meetup. I put it here. It's not, strictly speaking, it's not Rust, but Linz has such a vibrant JavaScript community. And Stefan, the organizer, together with me of the Rust meetup, he is the head of the Stahlstadt meetup, one of the heads. And there will be a meetup on the 21st of September, right?
Yeah. And we have just conversation.
Of course.
So yeah, we have a meetup on. It's my kid, big kid back there. So we have a meetup on September 21st, and we have about a couple of 4 talks or something. If you're not into JavaScript, there's at least some WebAssembly talk this time. So awesome. This is fantastic. Yeah. Alrighty. Cool.
Thank you very much. So this will be Stahlstadt.js. Stefan will be in person or hybrid or? In person at Karriere.at. Okay, very good. And I think the last one is Eurorust. I'm pretty sure everybody who is passionate about Rust has heard about Eurorust. It's going to happen in October. It will be online and in Berlin. And yeah, we are looking very much forward to this event. Stefan and I, can we already say it? Is it already? So I will be there in person. You will be there in person, and yeah, take a look at the talks. Maybe you will see some familiar faces there. Okay, very good. And that's it. That's the community news. That was my introduction. I hope I didn't take too much time. And I'm asking Lisa whether she is ready.
That's a good question. Can I get 5 more minutes?
5 more minutes. Okay. Then I have to tell you something. Any questions? Any questions here? I can tell you a little bit about the Grand Garage, what you have here, because that might be interesting, right? We are here in a historical place in Linz. It's called the Tabakfabrik. Tabakfabrik is called, in English, it is Tabak Factory. And it's called like that because years ago, decades ago, cigarettes were made here. It's a huge industrial complex here. And in this industrial complex, it was a big cigarette factory. And when they stopped making cigarettes here in Linz, the whole industrial area here was converted into a business area. Business area especially for technical companies and organizations and creative businesses like designers, web designers, marketing, web design agencies, and things like that. There are startup workspaces here, shared offices, and also this Grand Garage. The Grand Garage happened when another community here in Linz was looking for a new home. There is a community here in Linz which is called CAP. They're called captains. I'm not sure what the abbreviation is standing for currently. But what they essentially offer is they offer for pupils who are in high school. These students can do a technical education beside their usual staying in school. So what they did is they went to special education facilities where they learned how to deal with CNC machines, how to deal with robots and things like that. And many of these students came to the founders of CAP and said, okay, when I finish this side education, where can I try that? Where can I do my projects? When I'm out of school, I don't have these fancy robots at home. So what should I do? And this was the initial factor why the founders of CAP founded the Grand Garage. So it is essentially a place where young people can come to, also adults, of course, everybody who loves to build stuff, and they can use machines which they typically don't have at home. That's the whole thing. And just to give you an idea, we have here 3 or 4 stories full of machines. I told you already, there is a metal workshop, there is a plastic workshop, there are 3D printers, there are laser cutters, there is an electronic department, there is a, sorry, I don't know the English word, Glasbläserei?
Glass blowing.
Glass blowing, thank you very much. Glass blowing, you can do that here, and many, many other things with really expensive machines. And the student has only to pay, I think it was 15 euro per month, something like this, and they get access to all this infrastructure. So this is really a great thing And we are really grateful to have it here. And there are also some rooms for presentations, for meetups like this, for community meetups and things like that. And we often use the facility of the Grow Garage. So, Lisa, I have tried to cover 5 minutes.
It was beautiful.
Thank you very much. So now we have to switch between our laptops. Let's try. What could possibly go wrong, right?
Yes. I'm running under this model, like I've been running under this model the whole day.
I forgot something. In the break, we can we can provide some food. So if you stay here for the break and you think you are going to be hungry, we will order pizza. If it's okay for you, just to make sure, we will order vegetarian pizza. So everybody should have something. It doesn't matter if you are a vegetarian. If you are vegan and you want to have a vegan pizza, please let me know. But I have here a sheet of paper and a pen, and I will go it through. Please make a line if you want to have a whole pizza or a half pizza. If you only want a quarter pizza or vegan or whatever, write it on this sheet. I will gather it at the end, and we'll make sure that in approximately an hour, we will get some pizzas. Is that okay for you? Everybody fine with that? Awesome. So please just hand it through, okay? Lisa, are you all set?
Yes.
Okay, so I will, yeah, you need the microphone, right? Here you are.
Does that work sound-wise?
Just give me a second.
Yeah, okay.
So, could you please share your screen?
Yes.
StreamYard?
Definitely. Let me just... or maybe not. I need my mouse. That is probably... Thank you. I have... and then I can... no. Actually, it is probably... Oh, no, I can't. Here we go.
I think you have to press allow.
It's okay. Thought I needed to. Here we go.
Pull up your slides. And
Okay.
Very good. Lisa, I can add your screen and you're ready to go.
Thank you. Oh my God. It's so nice to be here. Hello and welcome. Just off the bat, I had several technical issues last night and just until now. So I will hope for the best, fingers crossed, but if things don't work out quite as well as they should, believe me, they did at some point. Okay, but this is the fun of it, right? This is Raspberry Pi baby steps in embedded Rust. So like really tiny, dipping your feet into this if you've never touched this thing before, but yeah, I don't want to actually like talk too much because I'm going to talk about this a lot. Who am I? A couple of people who saw me yesterday will know that what comes next. I'm Lisa. I'm a creative technologist based in Berlin. Creative technologist means that I like playing with technology, the fun stuff, trying to use it for artistic purposes or sometimes also useful things, and ideally combining the two. This is a picture of where I took apart like a little bubble toy that I got for cheap, hooked it up to an Arduino, and then had like fun with bubbles. It was like very popular with people. I've been around Rust and the Rust community since 2016, 2017, where I just like thought it was cool, jumped in headfirst and sent a proposal into a Rust conference. So you heard that Euro Rust is coming up, the CFP is closed, but maybe next time just like propose something, and if you get accepted, you actually have to learn the language. This is how I learned the language. And last November, I was like very, very happy like to be given the chance to organize Rust in Arts, an online conference where I tried to bring these two worlds together, like in an artistic, playful, interactive, fun kind of, or like all of these kinds of possibilities, plus Rust, because the intersection is there. Artists need tools. There's like more and more artists that can program, that want to like express themselves through either programming or just like any sort of technology that they can like get their hands on. So this is like very exciting to me and also to other people. And this was really cool. So this was me, but embedded who this. I still remember like the first time somebody was talking to me about embedded development years ago, and I was like, but embedded in what? Because like I couldn't really think about like what is this concept. Then again, if on Rust's like homepage, we see it like as one of the big like areas where Rust really shines. Like, you know, it's like embedded. So embedded is about like tiny microcontrollers, like various things. So my big area of let's call it expertise is in the Arduino world. So this is kind of like the hobby, the maker space. So like I don't build production things. I don't actually have to program machines that then build things like cars or whatever tiny else machines build these days, machines to build more machines. But like this is kind of like where I come from, where I learned a lot about electronics and like this kind of was dealing with in this space. If you've like looked into like maybe Rust and embedded, you've maybe come across this thing, because the new Rust embedded guide actually recommends the microbit, which is like actually an educational board. So it's meant like to be cheap, and like kind of it's very nicely designed and already has some components on it that you can play with. It's meant to teach people programming. And I'm like really happy that the Rust embedded book kind of like, or the embedded community picked this one up to like teach people embedded Rust. And actually only like recently discovered it, because the first time I looked into the guide, they were still recommending this one, like a more, I guess, hardcore board, like developer board with like, oh, it has all these things, and like, and I'm like, I don't even like. I'm a visual person, so with like, the website with like where you can order it is already kind of, I don't really know if I clicked the right thing here, and do I need something else? What do I need? So this was scary and not very beginner friendly, in my opinion. Sorry for touching the microphone. This is much nicer, so I'm happy they're going this route. But in the end, there's not just like these microcontrollers, like tiny, like single board things, but there's also like single board computers, like where the entire computer lives on a single board. You probably heard of the Raspberry Pi. It's very popular, even though they're now getting really expensive because like of production issues that probably people are aware of. But the cool thing is that, or like not the cool thing, but the thing is, if you want to get into embedded, you need some sort of hardware to play with it. There's emulators, but I think the fun is actually getting this tangible feeling of I'm programming, but I'm programming the hardware. There's something there. And I always go with like, use what you already have, because I have the feeling that most people who program have at one point in their life been given or gifted some form of Arduino or Raspberry Pi, or they kind of like lie around and they accumulate. So maybe if you don't have one, maybe ask a friend. They probably have one, because even I had one and I've never really done anything with it. So the one that I had at home is the Raspberry Pi Raspberry Pi 3 Model B. It sits up here. I will show it to the camera in the stream in a second. So I thought, okay, I know a little bit about Rust. I have the single board computer that apparently is also able to run Rust, and we can like do something with it. So let's do something with it. Just like this is the point where I'm starting. I have super little experience in actual bare metal programming, come from like web development and like higher level languages. And like, if there weren't so much Arduino related resources on YouTube and the entire internet, I probably would not have been able to build anything at this point. So I'm very, very reliant on like things that other people put out there. So thank you people who put stuff out there for me to learn. It's very cool. So like, yeah, little experience, not really sure what I'm doing, but I have a rough idea of what I actually want. And this is the motivating factor, because like once you know that you want to build something and you know it's kind of within your range of expertise, maybe, you can get there. It might be rough, but you can get there. What do I want? So for me, what I really, really want is physical computing, which is also sometimes globbed together in like a part of like a creative coding. So what we want is reading from and interacting with the physical world. So reading from could be collecting of data through sensors, some kind of like modules. There's like tons of stuff out there. And interacting with the physical world is basically then not like taking information in, but then after we did something with it, we want to influence the world through our code. And this can be lighting up an LED, which is already pretty cool because lots of LEDs make lots of cool lights and like various patterns. It can be really beautiful with just creating a little bit of light. But we can also like actually interact or like move the world through like motors and like different kinds of motors that I'm also going to talk about really quickly, and then have an impact and actually have our code magically, robotically do things in the world. So this is really, you can probably see that I'm really into this. So this is what I want to do. For this to work, I had to walk through a couple of steps that I actually had to do today, again, for technical reasons and bad preparation reasons. So if you want to do this, you can go one of two routes. You can develop on the device. So the Raspberry Pi is a complete computer. If you have no idea, it's a complete computer. You can put an operating system on it. The classic one is Raspbian OS, which is like a version of Debian. You put it on an SD card, boot the SD card, and then you have like a little, it's an operating system just like you used to. You can use the GUI or to use then the browser to install Rust, just like you're used to on your laptop or desktop. It's really nice. I also linked these slides will be online later. I also linked a video tutorial where like someone walks you through all of these steps. And then you can just SSH into the Raspberry Pi. So like I'm actually doing the same here. I hope the network will not shut down and like I lose connection, because that would be bad. But then you can actually like SSH into the Pi and then like run your Rust, compile your Rust, write your Rust there if you want. The other option is also cool because it like also highlights one of Rust's kind of like strengths in a way, is that you can cross-compile, so you can actually write all the code on your laptop and then compile it to a target for the Raspberry Pi with the Rust target add. So like if you've never, like the only target that I ever added additionally was the WASM target. So like actually adding another one for a microcontroller or for like an ARM device was actually also kind of cool to me. I also linked to an article where someone actually builds like a little like deploy cross-compile setup that is also like really nice. So lots of fun to be had. For this one, or like for the rest of the presentation, I will actually be working on the Pi, because yesterday when we like this little laptop here had kind of like some performance problems with like streaming and then also compiling. So I hope when I do the compilation on the board, where also pre-compiled things, we don't have to work for don't have to wait for forever to get results. Cool, lots of talking. Next step is getting to know the Pi a little bit, especially these little, what could be like a nice word for them? Pointy things. These are called GPIOs, General Purpose Input-Output Pins. And if you've never like touched anything like this, it might look like kind of weird, like what is the purpose of this? But this is actually the coolest part about the Pi, in my opinion, because through these little pins, we can connect them to our circuits, to the sensors, modules, motors, whatever we have, and read and write from them. General purpose input output. So this is what we're focusing on. It's kind of like putting little wires on these pins and then connecting them to our circuits. a thing that I didn't know, because it's different in the Arduino world, is that there's different kinds of numberings for these pins. Or like these pins have like certain numbers in software that don't really match with like how you would go and count the pins if you just look at it, and you would be going, or like you look at this row and go, okay, like 1, 2, 3, 4, or maybe you would go like per column. It is not like this. It has these special kind of names, which is why I recommend looking up these kinds of like sheets on the internet of saying like, okay, what are these actually called? Because the first time I tried this is like, okay, we'll see this later when we connect these, that I was like, it's not very intuitive, and you kind of need to know what you're doing. Also, which I also later learned, is that special pins have special functionality on the Pi. You see at the bottom here, different kind of like serial protocols that you can speak, like I2C and UART, I guess. I don't know how to pronounce them. That might be interesting to you. We will actually use one that is not explicitly labeled here, the PWM pin, but just be aware that like if you read some of these words somewhere, it's like it's protocols to like talk to several peripherals if you want. But this is not important to know right now, but maybe in your future. The other really important thing to like just quickly brush on basic electronics is the power and ground. So when we build a circuit in a second, we always want to like, we need to power, like we need to get our power from somewhere, and we need to like also basically close our circuit, like our circular thing, by like connecting it to ground again. So throughout these pins, we have several ground pins that basically all do the same thing, like give us access to a shared ground that we can use to like close our circuit. In my example here, I actually have a breadboard where I like pin this out, but I will go over this again. But basically now, red means where the current comes from, and then it like goes into the ground, and then we like attach things basically in between to do things. I hope like no like actual physics teacher watches me explain this, because this is probably really horrible. Okay, so we know a little bit about the hardware. We kind of know in the direction where we want to go. Where's the Rust part in this? Because I don't know how to like actually work with like registers and like how these do how things work. Like I will also look forward to Tim's talk later, because I'm pretty sure I will learn a couple more things about some of the concepts here. But luckily, there's people out there who've been busy writing cool libraries that we can use. I've been working with the RP-PAL. I think of it as like my pal in the Raspberry Pi world. Crate, so the Raspberry Pi Peripheral Access Library. This is a screenshot from the Crates.io page, but we can already see that we have all our favorite words here again: GPIO, I2C, PWM, which I briefly mentioned, which we're also going to use SPI, UART. So it's like, oh yeah, lots of things that we can use. Maybe later, we will only do a couple today, but I think this is actually like from my little research, the library or the crate that was the easiest to use and just worked. So my recommendation for this kind of endeavor. Okay, some electrical components that I will use and also quickly talk about when we see them is that I have a breadboard. It basically like helps me put together my little circuit. Some jumper cables, resistors. So like cables are just cables. Resistors help not adjust but regulate the current for some of the components. For example, LEDs might not or might break if there's too much current in the circuit. So like you might want to put a resistor in front of it just to like shield your components a little bit. We have buttons or switches for interaction, and motors or servers or steppers, like different kinds of motors basically to do cool things in our little projects. If these words mean nothing to you right now, I will show them to you. No worries. Okay. So step one. So this is all the prep work done. It's like time to breathe. And then we start with step one in our endeavor of like, okay, somehow interacting with this thing. And I called it Hello Blinky World. because I learned that in the world of hardware, the hello world is making an LED blink. This is kind of like the same thing, and I thought it's really nice. RPPal actually has the blinking light example in the README. So I thought, okay, let's just take this code and try to run it and make an LED blink. And I will attempt this, actually. Let's see. So this is the wind. Actually, let's do it differently, because I don't think I ran into several problems, and I have to like quickly. Let's do it like this. I think I will share the code that's on my laptop, and then run the code on the Pi, because I don't think I have an editor on the Pi that is not the default one, and I don't want to use that. Yes, trust all the authors. Okay. So this repository is also online on GitHub together with the slides, so you can like look at this if you want. I also want to like include more information about about the pin connection, because that's not really good right now. Feel free to ping me if you want to do this and you don't, or you get stuck with this, but okay. With that being said, is this big enough? Yeah, I think so. This is basically the example from the RPPal README, except that I replaced the error type with, or like the dynamic error thingy with anyhow result, but they don't have to worry about this. The cool part here is that we just can use some like standard library stuff like thread and like time components, or like time functionality. And then we get from RPPal just GPIO. So the base type to interact with our GPIO pins. And then we say here, and this is already kind of like the thing, we create a constant with the actual pin that we want to interact with. In this case, it's 23, and this corresponds to GPIO 23 in the diagram or in the thing that I showed you, and not the physical thing. So it's really the GPIO notation for this. And in the main function, we just print some device info from device info, which is nice. But then the actual thing happens here. We create a new GPIO pin, and then it's part of the API, we say get this specific pin that we want to talk to, and then we want to convert it into like basically saying that this should be an output, because we have to be explicit about do we want to use a certain pin for input or output. Default is usually input. So if we want to like write to it or like output something, we have to like say, hey, this pin should be an output pin now. And then the example uses a simple loop statement. And we have actually a pretty nice function that is called pin toggle. So we have two states, on or off, or let's say high and low, which is usually what is used in the hardware world. So we want to say where low is 0 or like false, and high is true, basically. So whatever it was before, we toggle between these two, and then we sleep for a little bit, and then we do the same thing again, which will result in a blinking LED. Exciting. Okay, I will actually go to this. So this is on the Pi, and I was I'm hoping I'm still here. It's not responding. Yes, okay. So I ran this, and now I will switch to this camera, which is this one. Yeah, does it work? Cool. So I have my setup over here, and I hope this works. So this is the Pi. Whoop. Oh my God. I need a higher resolution camera, I think. So this is the Pi. Maybe let's put it like this, because like this is how you saw it in the diagram.
Should we put the whole camera?
That would be amazing. Okay. Thank you, Stefan.
You're welcome.
Ah, amazing. Oh my God. It is very blurry. I am sorry. The important part is I tried to stick to the color coding if my cables permitted it. So red is positive, black is...
Ooh, a light. Does that help?
How many people does it take? No,
15.
15. Okay. Red is the positive, black is ground. And then for this example, the blue cable is actually the LED. And if you follow it all the way here, Stefan, can you move? Perfect. We see that I'm here on my little breadboard. Just a little explanation for this. Here on the sides, we have the blue and the red line that is indicated, which we can use to say, like, basically, I feed the ground into the blue line, which gives me access to ground in the entire line. Same goes for the red line for the positive current. So, like, I can access the entire positivity, like the positive current from there. So what I did then is I branched out. So where the blue cable goes, like all the middle parts. So on the sides, it goes from top to bottom, and on the sides, basically they go by row, which is something that is also like randomly or seldomly explained. So the blue cable goes into this round, which is I think labeled 6, but you can't read this here, which it shares with the LED. And then the other leg of the LED goes into row 8, where I put the resistor. So this is what a resistor looks like. And the other leg of the resistor goes into ground. So if we follow the circle of the circuit, we go in here, positive, then throughout this route, through the LED, through the resistor, and back into ground. What's the use of the blue cable now? This is where we now say from the Pi, write high current into this. Because like actually, if you've paid attention, and I didn't say it, that in this circuit we don't actually use the red cable yet. So the positive current in this example actually comes from the blue cable. I was talking too fast for my own good. Comes from the blue cable, goes into here. So every time we write like the toggle, we write either high or low, so like give current or not, and then we wait half a second. And depending on which state we're in, the LED is blinking, and it's blinking. Hooray! Cool. Thank you, Stefan. You get a better setup. Amazing. Cool. So with the blinking LED, we have like step 1 resolved. We could like write a little bit of something into the world, and first of all, make sure that we can actually talk to our GPIO pins, and second of all, be like, yeah, did our first thing in the real world. Amazing. This is the diagram again. Here's the connection again. So this is all documented, at least in the slides, if you want to do this again. And we ran it. Cool. Step 2, hello, touchy world. So we wrote something out into the world, but it's also, I talked about like reading from the world. So like kind of interacting, like we need to interact with something. And I chose touch because like I have this like touch sensor that I can also show you in a second. And there was another thing that I stumbled upon coming from Arduino, because the standard Arduino Uno board that you have has digital as well as analog pins. And what's the difference? Is that in the physical world, binaries actually don't exist. So everything is an analog signal, or like it has various, it's a range of things. So when we say it's either like we write to the LED and we either say high or low, what we mean is we go to the extremes of the ends of this current to make sure that we get a clearly discernible state. But in reality, we can like, we could adjust this, and we sometimes see this because you can dim light based on the current that you send through a thing. And the thing is that so the Arduino Uno can read analog signals, analog input. So like we can actually like get all this like finer grained information. But the standard Raspberry Pi can actually not. It has only digital pins. And I didn't know this beforehand. I was like, okay, this kind of is annoying because a lot of the easy to use sensors that I wanted to use actually rely on analog signals on inputs. So I was kind of like, okay, maybe I do use like a simple button, but then I realized that that this touch module that I have is basically what it does is, even though it's an analog module, let's say, that if you touch it, you basically close the current, and if you don't touch it, if you touch it, yeah, you close the circuit. I mean, and if you don't touch it, the circuit is kind of interrupted. And even though it's supposed to be an analog module, I still get the two states. So I could kind of like hack around this by saying, okay, this is enough for me to actually work with this. And I actually also have to keep an eye on time anyway. Okay, so to go the next step, reading from a touch sensor, I connected the ground and the voltage as we had before. A touch sensor has 3 pins, so we go into voltage and ground, and then we have the signal that we can read from it. I put it into GPIO 24, so like next to the LED, so I can, for this example, use everything. I will quickly look at the code for this one, because yeah, and it's similar in a way, as opposed to like the LED. So we still get the GPIO pin. I called into input, which I think is optional in this case, but just to be explicit that like this is an input. And then I wrote another loop where basically I want to say, or like read from this pin if it is high. So if it's getting touched, I want to print high, and if it's not getting touched, like there's no connection, it should print low. And then we sleep for a little bit in between so that we don't like spam we're going to spam our terminal anyway, but not so much. Okay, so let's run touch. It prints low. Okay, so this is working. And I don't know if you can switch the camera over to this camera. Yeah? Yeah? It's going, okay. So this is the touch module. It's really just like a little square. To see if I made a stupid mistake. No, but this should all be okay. Okay, maybe let's not use too much time on it. It was then part of my technical mishap from earlier. Believe me that it does, or like it did actually work at some point. But like I want to get moving to like not take too much time and like also get to the big finale. Because there's step 3 as well, because like reading to like sending stuff out into the world like an LED is cool, but I think it's super duper interesting if we actually start playing with motors, because they have so much potential and you can build a lot of stuff with them. And for this example, I actually brought a servo with me, which I'll show you in a second. It's a tiny motor that is actually like quite sophisticated in a way, because we can control exactly in which position it should move with just code. And this part of like method of telling the servo how to do that is called PWM, or pulse width modulation. And what we're actually doing is that like in certain intervals, which are indicated like always when we start sending a pulse. So this like in certain intervals, we send a signal for a certain length. And based on the length of the signal, the servo then understands in which position it should move to. If this is a little abstract, it will hopefully be clearer in a second. Just like for these tiny, cheap, like hobby servos that you get, the range is usually that it can move like from 0 to like a 180-degree angle, so like kind of like a half circle. There are also like now servos that can do a full like 360. So if you want something specifically like this, look out for it in the shop. But like usually this is like the 180-degree angle is what you usually get if you get like the standard average servo. They usually also come in packs of 5, like they're really affordable. Okay, the circuit for the servo is a little bit more, like only actually like a tiny bit more elaborate, let's say. For some reason, the cable the servo comes with, the VCC is also indicated in red. Ground is brown and not black for some reason, but now you know. And then another note that I wrote really like tinily in here is that usually if you have a motor and like they can also be like really, really big and powerful, you should separate the power supply from your motor from like the rest of the circuit and like the of the components that you work with, because when the motor starts working, it draws a lot of current, which can kind of like lead to like really like gaps or like disrupt like the rest of the circuit, and you kind of like want the stability, so you should separate this. For this little example here, it's fine, but if you want to like do something with like a big motor that pulls something, you probably want like an extra, like a different supply for that. And then we connect the pulse, which is the third pin on the servo to the Raspberry. There's another thing that I didn't know, and it gets our PPL gives you an error that I couldn't really connect from what was happening to what the issue was. Is that the Raspberry Pi provides hardware accelerated pulse width modulation, which is really like accurate and fast and cool, but you have to enable it first. But there's actually a section in the RPPAL documentation that tells you how to do that. So that's if you get like I think it's just permission denied, and I was like, what kind of permission? This might be related to this. Okay, quick, let's run through the code so that we can get to the finale. The biggest difference is that instead of GPIO, we now get PWM, and then we get channel polarity and PWM from that. And these constants are important because they depend on the kind of servo that you have. So these are the units for the standard, like the little blue servo that you see in a second, where the period in milliseconds, like this value is kind of like the frequency in which we send the pulse. And then, we can kind of deal with that neutral precision, but like this is basically the length of the pulse signals that we then set, like that give us the position of the servo. So the minimum pulse length is 500. It's not milli, it might be microseconds here, actually. I'm not sure. And then this would be 0 angle. And then the max is 2,500 microseconds to get to the 180-degree position. Okay, now that we know that, we can go to main and initiate our PWM with period, where we put in all this information from microseconds, and then the period is in milliseconds. What polarity means in this case, I am not sure, but I just put it in from the example, so it works. So what happens is that we initialize this, we sleep for half a second, and then I say, hey, send a different pulse, so like set pulse width, and then we move to the minimum, so like the 0 angle, then we sleep again, and then we do this little loop that basically says, oh, then walk to, like for minimum, walk to the neutral position in like small steps, so it looks like it's a little rotating. And I will actually not start this right now. Can we also get the camera on the setup again?
Of course.
Cool. So this is a little servo. They're usually like very small, and they also come with different kinds of these little things to put on top, different kinds of arrows. So I use this one because it like clearly indicates like where we're going here.
Lisa,
Yep.
could you put StreamYard on your computer, because then everybody in the audience here in Linz can also watch.
You don't see it. No. Oh gosh. Well, let's do it like.
Just to take the stream, yes. Awesome.
Okay. And then.
Don't do anything. Just show again the.
Okay. Let's do it like this. Okay. This is the servo. Cool. It's very small. There's all the logic and all the electronics are actually inside this little thingy. You see the cables coming out. I placed the important cable that sends the pulse in. Whoa! Now it detached it. Damn it. Not good. Put it on here. And then I will try to run the code and like hold this, and you can see what's happening. So remember, it will like walk through the positions automatically. Oh my God, I will never do this again. This is too much. Did you see it? Should I do it again?
Yes.
Yeah? Okay. So we start with the Mac. Yes! So we started with Mac position, then switched to minimum, and then like we iterated over the top. We have everything now. So the only thing that's missing really is a creative idea with like what to do with this stuff. And I'm probably way over time. I'm very sorry. But I don't know if I have a slide for this actually. Let's see. Bring everything together. Okay, let's do this. So I need to do a little bit of rearrangement because I only have one Raspberry Pi with me. So I will quickly unplug all of these and then build up this piece here. All right.
Can you switch to StreamYard?
Yes, I am sorry. This. So. This is here. Oh my God. We can do questions while I do this, but only easy questions so that I don't have to think too hard.
How many pulses do you need to send for the motor to go to a specific position? Is one enough, or is it?
One is enough to move, but it will, like, it kind of requires, like, the frequency, you have to keep up the frequency anyway, right? Also, like, we change the pulse once, but the pulse is actually constant, so it's not actually to what I said first. We need the constant pulse, but then we keep it at the same value for that. 1, 2, 3, 1, 2, 3 here. And this should be here. And this is 1, 2, 3 here. Oh my God. Where does this one go? Oh, here. I believe this one goes here. Stefan, is there my notebook there? No. Ah, it is in the front, actually. Perfect. Where I put my little cheat note in case I forget everything. This is the servo.
Can I borrow the mic?
Yes.
For a second, then I can give you a few minutes.
Thank you.
While Lisa is preparing the rest of your demo, I have a surprise for you. I hope you will like it. I asked the Grand Garage people to do something for us because we're here in a makerspace, and so we have something for you. And I will try to show it to you here. Can you see it? Can you see it? Can you see it? Can you see it? So you will get your very own special laser-cutted Rust logo with the Linz thing and so on. So I hope it will come out of the laser cutter in time. I have one, and we get 20 of them, so everybody who is here should get one. I hope it will be done in a second.
Cool. I'm also almost done. I only slightly confused myself with 1, 2. Then touch. Okay, this should work. Hopefully, and then let's get. Worked yesterday. Okay, let's go with this. I will hold this like this. So, maybe we can even do it. Very professional of me. Okay. So I built a little game with this. It's a complete hardware game, and I built a beautiful interface out of cardboard and a little bit of gaffer tape. It travels very lightly. That's nice. So the idea is that you're kind of like trying to crack into a vault or something, and you have to like guess 3 random numbers in sequence. And if you indicate it as indicated by the 3 blue lights at the top, the servo arm will kind of move from 0 to 180. And in the background, every time it is close to the randomly generated number that we don't know, the yellow LED will give us an indication of like, oh, we're close. And then if we're close, we need to tap the touch sensor. And if we're fast enough, we basically crack the code, and then once we have all 3 numbers, we get the light show. My only worry is that the touch sensor might not play well with us right now, but let's see how it goes. Let's play it. Hopefully, damn it. I called it Panzerknacker, and I couldn't write it Panzerknacker. Okay. Wrong window. Okay. So what happened in the beginning, if you maybe heard it, is that it did a little configuration. And I also did the LEDs are in the wrong order, but this is fine. You can see the servo just like ticking through the individual steps, like one by one. And once we get close to the secretly generated number in the code, no, it didn't. This might not be the case that I just don't get the correct touch signal or was just too slow, or there's a bug in the code anyway. Let's see. Okay. something happened that wasn't supposed to happen. But this is the idea of the light show in the end. This is like a quick example of just like throw everything together. You can play it later. Maybe when it's not live, it will work magically, much more reliably. But just to give you an idea of the code, how does this work? Basically, I threw it all together, made a little game state struct to keep the data in place. We have like, also like a little state. So we have like this little setup configuration, then the actual play loop, and then the win that plays with the, just blinks all the LEDs. We have a lot of setup code. Then we have this little bit random number generation, setting everything up. And then actually the loop that I'm using with is just like matching on the states. So instead that we set everything to low and sleep, and then do a little servo movement just to see if everything works. And then in play, I'm actually like matching on like the current LED is kind of like indicating which state are we in right now. So like if all LEDs are like blinking, like they're all like high, this is kind of like the indication that we actually won. This is the matching on the current number. I just like use a little bit of wiggle room with like the actual number, because like we can't actually be that precise with the movement. But basically, once you match the number, we generate a new one, and in like start blinking another part of like the next LED. And this is like a little bit of logic to make the servo move in one direction until it hits maximum, and then like move it in the other direction. And then the code for the light show. And this is it. It's not that much. It's also not that pretty, maybe, but it like gets you there to make a little hardware game. And that's fun. You can make it like in a little box and just put a cable in there, and then people can play it. This is it. Wow, I'm so excited. So this was baby steps, like just like mostly dealing with electronics and minimal part on the Rust embedded side. But I think it's a super nice way to like just ease into, because like, we can write code as we're used to in like a not embedded environment, and just like go from there. I put up a couple of videos, especially the one by Marco Amann, who's like, I think it was also like a Rust Linz session maybe, where he goes from like 0 to no standards, like actually going a fully bare metal. So like if this is more like the way you want to go, check out this video. And then I can only say vielen Dank, and then I'll finally stop talking. And thank you very much.
Thank you so much, Lisa.
Yay.
Can I have a mic for a
Yes.
second? Thank you so much for this awesome talk. Thank you. And now, for those of you who are in the room, there is a very important guest here. Clemens wants to tell us what comes next. Clemens, what are we going to do?
Stefan.
Exactly. Stefan is currently fetching some pizza, and we are going into the break. So for now, exactly, Papa is coming with the pizza. Very good. So for those of you who are in the streaming, we will have approximately 30-minute break. And in 30 minutes, we will have our second talk. So grab something to eat. Also at home, grab something to drink. And make sure to be back in approximately 30 minutes. For those of you who are here, enjoy the pizza, grab a drink, and we will continue in 30 minutes. Thank you very much. Thank you, Lisa, again. Thank you very much.
You should, yeah. Hi, this is Tim McNamara. I am the author. Can you hear what I'm saying? Hopefully we won't have another dance party starting. That was fun.
We already screaming.
I think competing with the music outside was a bit difficult. I want to know about the setup because hi. I want to be able to recreate this in Wellington.
Could you please just announce that we start in 5 minutes or so?
Hi everyone, my name's Tim. I am the second speaker. We'll be starting in about 5 minutes time. Just going to finish off some technical issues. We're just checking that all the technology will work for the next talk, as well as bring everyone in who's just had their pizza. So if you have been waiting, well done. I'm looking forward to presenting very, very shortly.
This is going to be fun. Let's see if I can make a full sentence until yeah.
Habt ihr alles erraten?
Ja, ich glaube schon. Danke. All right, so just a second, Clemens. All right, we continue after the break. I'm so sorry.
Wir machen noch eine Frage. Der Stego hat. Kommt der Stego mit den
So.
hier.
So, jetzt bin ich dran.
Hey,
Na, so. Geh dann. Give us a second. Yeah, no, it doesn't take long. Alrighty, so without further ado, no, I'm actually, Clemens ist Stress haben, okay? So, Rainer, kannst du machen? Ich glaube, das kriege ich nicht hin. So.
Happy to hear. Okay. Welcome back after the break. We are going to start with our second talk. Tim is our guest today, and we are very much looking forward to your talk.
Thank you so much for the introduction, Rainer, and auch Stefan and his little boy, who is actually a lot cuter than he is thinking right now. I think he's not very happy with his son. I'll just plug this in. Okay, cool. Hi, everyone. It is really lovely to be in Linz. I have traveled not to Austria from New Zealand, not just for this talk, but I thought that while I was coming to coming to Europe, I should definitely come across. I really enjoyed presenting remotely about 12, 18 months ago, roughly about that. And I just sort of wanted to repay or just sort of say thank you because I really enjoyed it. Now, we are going to the question of like who, hopefully this is legible. Who am I? The easiest way to find me, yeah.
You're not sharing the screen StreamYard. I don't know why.
Hello, okay, I'll just need to fix the technical stuff. We need to playing. Share. Oh gosh. Into the studio, share my screen, select entire screen, allow. Are we good? We're good. Okay, so that was a wonderful introduction. I won't go through it all again. Boxes, heaps, and stacks. What we're talking about today. Who am I, first of all? The easiest way to find me is on the internet as Tim Clicks. And this is the book that I've written, which you may or may not recognize. Okay, so this seems like a talk about Rust, but actually, it's really a talk about computers, because this talk will only make sense if we explain not just the syntax of box and referencing and dereferencing, but also actually what those mean and what a computer is doing when it applies those operations. At the end of the talk, I would like you to know more about what a stack is, what a heap is, as well as other things like pointer, reference, memory address, what the ownership system is and what the lifetime system is, and one or two other things even. In this room and on the live stream, there will be people that actually know a lot more than me about these topics. So please do participate. Feel free to interrupt me during the talk or ask questions on the live stream. You're very welcome, and I'll do my best to answer. Or at least put it down as something that I need to learn about. So just to be very clear about which type of box we are referring to, it's this syntax you would have seen in Rust with a capital B box, and we have less than and greater than, and then some type T in the middle. Normally when we create a variable, we'll have the variable name and maybe sort of an optional data type, and then we create something. We have sort of the value on the right side. But when we put things in a box, we've got this different syntax where we start with the box and it's a new. And then this kind of magically works. And what's going on there is the essence of this talk. Because creating a box is different because it allows us to link two different parts of memory which enable dynamic memory allocation, or enables data structures to be created that can grow and shrink like string does and like vector does. But first I want to just provide you with some permission for like not knowing what is happening. So I want to explain my own learning path by just explaining how, when I was thinking of this metaphor, I was wondering like, what do we mean by box? I assumed, because before I learned Rust, I spent about a decade or a little bit more in Python. And I assumed that box must mean something that could like open or shut, or perhaps it was, maybe there was like a byte at the start and a byte at the end, some sort of tag left and right, and then the value was in the middle. None of that is true. Absolutely none of it is true. So I had the completely wrong mental model, which is quite useful when you try and learn a language where it's kind of essential. But like the first place to look perhaps would be the standard libraries documentation. The point of there's one sentence, which is a box is a pointer type for heap allocation. That's no good unless you already know what pointer type means. You need to know what a heap is, and also you need to know what a memory allocation is. Without that prior knowledge, the sentence is meaningless. So, and it turns out that actually I think that there's one other really important part of this discussion, which is the ownership system as well. Because the box takes ownership of the value that you're giving it. It's one of its essential. So if I added my own addition to that sentence, I would include explicitly that we're talking about the ownership system as well. So we've got this problem that before we can answer what a box is, we've got some further questions like what is a pointer? Because we need to know what a pointer type is. We need to know what a heap is. We need to know what a memory allocation is. What's an own value? Okay. Let's define pointer as a memory address that a compiler has for which the compiler has information about the type that the pointer is referring to or the pointer is pointing to. So I am an integer and I have a pointer over here that is pointing to the integer. The compiler knows the width in memory that the integer takes up in RAM. But I've actually introduced some new jargon. So now we have a new question that we need to answer. What is a memory address? A memory address is a number that the CPU or the computer hardware can actually use to translate to some place on a physical chip. The mechanics of how this happens is a few degrees beyond the scope of this talk. But essentially, your operating system and your CPU work together to convert that number into a physical place in RAM. So I'm just going to say it's sort of what that means. So we can think of a memory address in x86, 64, in the particular CPU architecture that you're unless you're doing microcontrollers, which we just saw earlier, is between 0 and 2 to the 64 to the -1. At least we've got a little bit more information to be able to define what a pointer is. A pointer is a memory, there's some length, it's known at compile time, and the first definition was a pointer type for heap allocation. We've got 2 out of 5 questions answered. So we need to now answer, like, what is a pointer? All of these types are actually embedded the same way. So this first one here is a reference to T, or what we call a shared reference to T. And this ampersand mute keyword is does anyone know what the term for this is?
Unique reference.
Yeah, so there are 2 terms. Unique reference would be the C++ terminology, and in Rust we tend to use the term mutable reference. They actually mean sort of the same thing. And then these 2 are a little bit different. Const T, and I'll just get rid of that. It didn't quite work. Const T and mute T, or with the stars. These are raw pointers. And lastly, so the raw pointer is less useful to most Rust programmers. I have fn. It turns out that functions are actually pointers as well. But instead of pointing to data, they point to some space in memory that has been marked as executable. The CPU encodes program code as integers and in-memory addresses as well. It just happens to execute them. Now, I'll get out of this. But we actually are really interested in this bottom one, which is box. It has the same internal representation as all of the others. They actually live, they actually look to, in the final binary, as exactly the same thing. This is what we call a zero-cost abstraction. The added semantics that we get with box, which involve its ownership of the value inside it, are a compile time construct. Many of these types are called references. I've been using that terminology without defining it. So now we have another question, like what is a reference? A reference is actually a pointer that also has lifetime information. So what do I mean by a lifetime? If I imagine a program started at 0, and then at the end of the program, when it exits, it's at 10. A value might be valid from point like time 2 to time 5. And if I attempt to access that variable at time 6, 7, or 8, those would be invalid accesses. Or if I had started to access it before it had been initialized, say at T1, that would be invalid. The compiler actually does a similar thing with lifetimes. Rust's difficult syntax, the reason why Rust requires you to sometimes use lifetime annotations is because it uses this information to guarantee that you will not access memory at the wrong time. You can't access some value before it has been initialized. That is, you cannot access a variable before it's been defined, like if the name doesn't exist. And you will get an error at compile time. By the way, and as a Python or an ex-Python programmer, this was very, very handy. I don't have to worry about name error anymore. We're like creating a bit of a stack of questions, which is slightly intentional. So we've got this definition of a lifetime of t is some span of time for which accessing a reference to t returns t. And by t there, I mean a value of some data type. Now, if you are a systems programmer, or if you've used C++ or C or some other systems language, and you know what a stack frame is, one thing to note is that Rust's lifetime system actually is bound to the stack frame of the function. But I think it's an interesting thing to explore, and I invite you to do so, but I'm not going to talk more about that because I don't want to scare people who don't know what a stack frame is. We have most of the questions answered, although we keep adding more questions. So I don't know, hopefully we'll get to the end. We now need to answer this one, which is like, what is the heap? I'm going to answer that by introducing another piece of jargon, which is the stack. So that's a problem. The stack is so we've talked about an address space. So the address space is this region of memory between 0 and 2 to the power of 64. And the top of that address space, like right up towards the maximum value, is where the stack lives. And right down the bottom towards 0, although not including 0, actually, is where the heap starts. That is only relevant in the sense of if they collide for some reason, that's actually a big problem. And in fact, there are protections in place to make sure that your stack doesn't grow too large. This is where the term stack overflow comes from. Anyway, I should start defining these terms. The stack is a region of memory of the address space that is reserved for function calls. It works really, really quickly because its memory model is very fast. Everything that exists in the stack is of fixed size. Additionally, there is actually some hardware support for the stack. There is a CPU register called the stack pointer, and variables that live inside the stack tend to be very small. So what ends up happening is a lot of the CPU cache, or a lot of, if you call into a function, you'll typically keep all of your variables either in registers or in a CPU cache that's very close to the computer. And if you are a language like Rust and you really care about performance, that's where you want your data to live. Because the alternative is that you have references and pointers, and that means that you have some memory address in some other part of the address space that you need to jump from the top of the address space down to the bottom, and then find the part in memory where you're referring to, and then you'll come back and forward and hop around. And that kind of hopping, or alternatively, you can go even further. We have references to references to references. This is a very slow process that involves like a lot of accounting. There's a lot of extra work that is involved for accessing memory from the heap. There's actually so much extra work that it's configurable. If you want to really look into this, the Rust provides the ability for you to control how the access works. This is called an allocator. And one other thing to note, just because it was relevant to the previous discussion, is that microcontrollers typically don't give you access to dynamic memory, or you don't get a heap. You only have a stack. Everything needs to be of fixed size. So you can think of a pointer, or like you can think of the box type as kind of a link between the stack and the heap. It provides you with the ability to access this very flexible address space, but provide a very, but keep a fixed size reference inside the stack. So our functions are always in the stack, but when we need flexibility, because we want a data type that can shrink or grow, or for some other reason, because we might want to share references between functions to some memory, it needs to live in the heap, then we need some kind of way to refer back to it. And the box is that type because of its ownership semantics. I'll just talk quickly about what a memory allocation is. That's a request for memory from the operating system. And the ownership system was the last one too. Was there a question?
Well, the last expression, it has a little asterisk to it, right? So you don't necessarily go to the operating
Right,
system.
okay, yeah.
It depends.
It depends, right? So I put sort of in a couple of the other ones, but I didn't hear. Now, the point was just for the just so that we get it in the microphone, that we don't always get it from the operating system, or at least you might have asked for, say, 10 kilobytes previously, and then you decided to tell the operating system that I don't need 2 kilobytes of that, and then subsequently you asked for some more memory, but you already had it available. And this is what I mean by, so you could think of a very simplistic way to implement this would be to always ask for more memory from the OS. Alternatively, you could be smarter and try to group requests for memory of very small data types into to a single larger request, because presumably asking for memory from the OS is going to take some time, and so we don't want to do that very frequently. So this is configurable, but it's a complex, difficult subject, and maybe I'll just put a hidden asterisk in there.
It's true for the default.
Yeah, it is true for the default case. Right, yeah, okay, yeah, that's right. It's always tricky when you try to write a talk for hopefully a general audience without scaring too many people. Hopefully there aren't too many people who are just more confused at this point. There is one final concept that we should define, and this is ownership. And this is like the easiest thing to define in the whole of Rust, right? No one has any issues with borrowing or owners. Okay, so like, what is an owner? In Rust, so the reason, I think this is another metaphor that is difficult because it does not match our intuition for what the plain English definition is. If you look in a dictionary for property and owner, it will probably say something like has exclusive access, or the ability to, if I think of property rights, if I own my house and like its little piece of land because I have like a little single family house, I can tell people who don't belong there to leave, and they would be required to leave by law. And but that has no association with property or ownership in Rust. The owner does not have the ability to say, no, you cannot access this, my data type. In fact, even when you, even if you are the owner and like your scope is the owner, and you have a method call, you'll notice that all method calls have the ampersand mute self. So you still actually need to borrow from yourself. And this is because the only thing that the owner does is safely delete everything that it owns. So you could think of, and that is the owner, when it is dropped, it calls drop on the things that it owns. The end. That's all. The owner has no special power. They can't go to court and force your data to come back. You cannot go. So now we get to go touch a little bit of code. I wanted to show the difference of, I've got A here is our kind of normal 1, 2, 3, and B is in a box. And hopefully I can, and I'm just going to click playground link. And if I create a main function, and then I call math, this should fail to compile, hopefully, as long as I know a little bit about Rust. So what this is saying, first of all, is that it doesn't know how to add a value of, let's say this is, we guarantee, let's say we say it's an I32, and this one here. So the values in these are the same. So it should, in principle, work okay. It's saying I know how to add lots of other things, but I don't know how to add these two types. I can't add I32 to a box of I32. In fact, we need to add a star, and this is not a multiplication. What this is a request is of Rust to go follow and get out what is inside the box and bring its context back into local scope. It's called dereferencing. So now we get a different compiler error, which talks about the, I need to print. So we should, this is all fine. So using box can be a little bit clunky, or like can feel less comfortable because you kind of get these kind of syntactic problems. But I wanted to show you, and we can put in anything that we want. Oh, actually, I will get to the next slide because it's important. Like, why would we do this? The standard thing that we want to do is like, why would we use a box, is to return a reference to some local variable. So we could assume that we've got some difficult or complex structure. Oh, this is, sorry, I had a typo. I meant to change this. I can create a which is some difficult or large thing. and then I can place it in the heap. So A is at first a local variable. And then after I call box, this difficult or large object is sent to the heap. And then a pointer is returned from the function. So just an integer comes back, but actually this difficult thing actually moves to the heap. And the good thing about the heap when you're dealing with functions and references is that the lifetime of difficult or of A is no longer bound to the function call itself. So normally if this was not here, if I was just returning large, the caller, the function that called build, would be the owner of large, and then when that function ended, or when the variable came out of scope, it would be deleted. And yeah, box provides us a little bit of flexibility. We can also use box to create a vector of trait objects. Now, the difficult thing about a trait object is that it does not have a size that's determined at compile time. So what this is saying is like, I want a vector. We can think of that as a list of box din display. Does anyone know what is happening here? Hands up, we've got 2 hands at the back.
We want a vector with structured implement display.
So right, so we're saying we would like, this is a vector of objects that implement display. So if we had this, and this pattern is actually implemented I found it in GitHub. So this is quite hard to read, sorry. You can see here that this person has created, it's in line 25, sorry. They have a trait of fuzz target. So this is and the specific types that exist within this vector are all different sizes. But because they implement fuzz target impl, they can all live in the same vector. Rust does normally not allow things of different types to be in one vector, because it likes to know of exactly how wide everything is in RAM, because its preference is to put things on the stack, because the stack is faster. In this case, if I go, I might play around with this. Sorry, I keep irritating the people with the mic. So I've got some vector, and I need to create an immutable vector, and and this is answers a bad name. Let's say it's like printable things. Ja, super. Okay, so what we're trying to do is create a function that, or some object that standard, I think it's standard format display. So Rust will allow me to use the absolute path in the names, saying it doesn't need to be mutable, saying you never use it, buddy. There's no need for it to be mutable, but it's a valid code. It will actually compile and do nothing. So thanks, Rust. So we can push our friendly 1, 2, 3 vig, and also printable. I should have given it a short name. Push a character. And I would like to just add an emoji in there, but I don't have one. So ampersand, an @ sign will have to do. And it's now saying that you need to actually put these in the box because you can't actually put the objects in there directly. So you're cheating.
This error message is so nice.
One of the things I really like about Rust is like it can be a better programmer than me. Like I don't need. I honestly feel that I learn. Like, one of the things I like about the Rust compiler is like it feels like a coach to me.
Reference is a book.
Yeah.
It's lovely.
It's really nice. Well, the box is such a common. It's such an important part of Rust that it's useful to be able to, or it's important to be able to give really helpful messages. Now I'm going to change things just a little bit because I want to show what happens if you, let's say we've got our difficult type again. This time it's not large. In fact, it's 0 size. And I'm putting this in the box. First it's saying, so it's saying that difficult does not implement debug. And what that means is the compiler doesn't know what I want when I tried, so I can't just, the compiler doesn't know how to convert difficult to a string. And so it won't allow you to put anything into any vector. Instead, you need to be able to you need to actually do what you've said, which is like only rely on the trait that you have defined. The other thing that's important is this trait object will only implement one of them, even though debug, I think, relies on display. Or does display? No, I'm going to stop there.
It's independent.
Yeah, they're independent. I should stop kind of going off track. One other thing that you may wish to do is that they've got A, B, and C here. And let's say we want, and this might be, say, small, medium, large. And then I want to provide some sort of other category. Now, if I have multiple selection variables, how much memory, this is 1 kilobyte. So this is an array of 1024 bytes. Now, you should only need 1 byte to encode all of these 3 because they, in fact, just any bit pattern that's different will be sufficient. But you need 1 kilobyte here. So if I had multiple variables, like S1 was selection small, and let S2 is selection medium. Counterintuitively, this will actually take 2 kilobytes of space because Rust will always make them every enum the same size, and the size must be able to fit the widest or longest variant in the, must be able to fit the widest variant. And so if I put box, suddenly the size goes down to the size of 1 box, which is 8 bytes. There's a question at the back.
Isn't this only the case if it's mutable? Because as long as I can't edit it and I directly assign a small, it should be small.
That's something I'm going to check, and that's a very good question. Let's say that I have 2 immutable variables, like these 2 here, and I only ever create those 2. In fact, I essentially never use large or other. If I comment them out, my code will still run. So effectively, they're irrelevant. The question is, in that case, is the compiler not smart enough to just erase this large variant and just use the smallest or the type of what you've actually used? Because these are all immutable variables. Isn't that enough? My understanding, and I want to double check this, can you please correct me in the comments if I'm wrong, because I'm going to say something that is likely to make someone like perk up. Okay, first of all, when I'm talking more about Rust here, so this is a little bit off topic, but immutable in Rust is a lie. When we use this term, we say mutable and immutable. Now this is false. Rust, because immutable variables are still mutable. That's why we have this notion of interior mutability. What? Okay, so allow me to explain if I may. So immutable works conceptually most of the time, but what is actually guaranteed by Rust is that two unique references or two mutable references will never exist. So there will never be two writers of the same data. If, however, you are if you own the, I'm getting myself into trouble. If you have that the mutable reference yourself, or maybe its owner, if you can guarantee, and this is what cell does, the cell type provides interior mutability. You can swap what is being referred to, and so it can pretend to be immutable, even though things are changing underneath. Now, that still doesn't completely answer your question, because you said to me, but Tim, you will never use that variant in your entire code base. I still think that, I know that you'll get a compiler warning saying these variants are never used, but I don't think that Rust will erase all of the access to those unused variants. Like, I don't think that it will create a type that is different than what you've written in source code. Now,
I
yeah.
think the only way the Rust compiler is allowed to delete the symbol if it's unable to inline every case and there is no unsafe functions and no references away from it. Because everything else, either you can swap it or C can do weird stuff, and only then you can save the whole space, but then the symbol will completely disappear.
Yeah,
But anything else, it will allocate the full kilobyte and a byte. And if you have 4 of these on the stack, your program will just randomly crash in the default runtime under Windows, Linux, and Mac.
Yeah. Okay, so I just want to get some of that on microphone, so hopefully I can replay this correct. So the Rust compiler will only erase code, or will, if it can, under certain guarantees, and those guarantees include the fact that there is no unsafe, there are no other references into the data, but essentially, even if you never use large or never use other, Rust will still is required to assume that somehow other might appear in your program, and therefore will include the whole kilobyte. Alternatively, this is a much more niche area, but if you write a compiler or you have lots of intern strings, you can save a wonderful amount of like 1 byte. Oh, sorry, no, 8 bytes actually. 1 word width of by using a box2 str, stir with a little case s, rather than using a string. And like you say, well, what is a box to a string? Or little case S string. This is a span of bytes that is guaranteed to be UTF-8. There's a massive downside to going with the box, and that is you cannot mutate the box. Like you cannot mutate the string. Or you can't grow it. You can modify the data that you've got internally, but you can't actually go and change it. Okay, box, by the way, is also the basis for collection types such as vector and string. String, by the way, is a vector as well. Actually, there's a massive asterisk there. It's actually not box. If you go and look in the internals, yeah.
Just got a warning that your battery's on.
Yeah, that'll be a good time to finish. No. It turns out that because of some really nitty-gritty internals, the implementation is a little bit more complicated, but conceptually it works. And but the biggest thing you will see Rust box being used for is recursive data structures. And if I wanted to implement a linked list in Rust, I would call for box, because otherwise, if I didn't, oh, that's the end, I would try to create a type that's of infinite size. And with that, I think we'll skip the looking through the other sections of the books. And I shall say thank you and done. Happy to answer any further questions. And I guess I'll stop. Oh, no, there I am. Okay, I'll stop sharing. And, like I'm doing my own computer art. I should be on the I should be at the festival that's happening on this week. Oh, and my computer's actually shutting down now, which is good. Should I wrap up or questions, queries, problems?
Have you ever worked with tagged pointers?
Well, no. Well, so the question was, have I ever worked with tagged pointers? And yes and no. Can I say that? So it turns out that in Intel, so this is like geeking out totally. Intel looks like their pointers are 64 bits, but actually they're less. I think they have an address space of about 48 bits, and so there's some spare bits right at the end that can be used to actually give the pointer a type statically. There are also some, I haven't implemented a programming language, but that can be used to do so. And I haven't done much at that level myself. Further questions? Hopefully, who feels like they have more knowledge when they started, like now versus where they started? One person that's successful, at least half the room. I'm happy with that. If you're very confused, I apologize. I'm happy to talk afterwards. Thanks very much, Lorena.
Can I ask you for the mic?
Oh, absolutely. No, I'm going to walk away.
For wrapping up.
Sorry for doing the mic.
No problem. Thank you so much, Tim, for this super interesting talk. It's always interesting to listen to people, how they describe the difference between stack and heap. I am a part-time teacher myself, and I try to describe the difference between stack and heap to students over and over again, and it's so hard. It's really hard. In fact, two of my foremost students are sitting here in the room, and I could ask them whether I did a good job or not. Okay, so everybody who watched us in the stream, thank you very much for watching us. Everybody who is here, thank you for coming. Thank you for coming to Linz. Thank you for coming to the Rust Meetup Linz. If you have another few minutes, you can stick around. The fridge is still not empty, so you can have a final drink before you walk home. Drive safely, travel safely. Lisa, have a beautiful holiday. I think you are starting your holiday tomorrow, something like this. And with that, I think we should wrap it up and say thank you, have a nice evening, see you next time. Bye.